So 7.1, Introduction to Radicals, which is, I guess, a little bit of a new vocabulary for us. But radicals, we have seen them just a little bit in that last unit, right, when we looked at difference of squares. This particularly is a square root, okay? And I don't know, there's some nerdiness going on in here, but a square root, if you look at square roots, this is kind of our most basic form of roots, like this one. And it does kind of look like a long division symbol, which maybe I didn't draw very well, but I did my best, okay? When you see a square root symbol like this, all it's asking is what number multiplied by itself is, I guess, the number. If the number was in the square root here, okay? So whatever that number is, and I guess a common number here would be like 100. Okay, so if you saw this reads the square root of 100. You'd ask yourself, well, what number times itself is 100? Okay. Now, of course, I think everyone understands that that would be 10. But 10 is only considered what we call the principal square root. It's not the only square root of 100. There's another one, and that is the negative as well. Because, as we know, you can take 10 and multiply it by 10 to get 100. But it is possible not just to take 10, but also negative 10. So, and that's just the opposite, right? Negative 10 times negative 10, it still equals 100 right here, okay? But again, the principal one is just the 10 by itself. And yeah, if A is not a perfect square, whatever the square root of that you're taking, if it's not a perfect square, then it's usually an irrational number. We can represent these with square roots so that they don't look so nasty. And we have seen some perfect squares already. One is a perfect square, 4, 9, 25. Oh, I forgot 16. There we go. 9, 16, 25, 36, and the list goes on. But that's right. I start with 1. 1 times 1 is 1. 2 times 2 is 4, and so forth, okay? Now, if you could memorize the first 10, at least the first 12, I would say, perfect squares, then a lot of this, I think, goes pretty smoothly, but we'll see that there's other methods, too. All right, this is all square roots of 81. Now, if this was to show it with the radical, it'd be the square root of 81, like this. Okay, now, of course, this 81 by itself is a perfect square, and that would be the result of 9 times 9. So 9 by itself is a square root of 81. But again, it wants all the square roots, so negative 9 would have to work as well. This has 2 answers, kind of like the absolute value equations that we saw earlier, where we had 2 answers. These ones now have 2 answers as well, or even the polynomial stuff, where we're able to factor those in equations. Then we found two solutions there. Square root. Okay, so square roots, and we do use the word square. It's really it's kind of like a power of 2, if you will, kind of thing. But yeah, it's like saying if you got a square here, let's pretend like I've drawn a really, technology worked. That's supposed to be a perfect square by technology means. Now, usually you would say this, if this was a rectangle, you'd say length times width. But the unique thing about squares is that the side lengths are the same. So you get something like this, and then you say area equals side length times side length. And as much as you guys want me to put the other s there, I'm just going to put squared, okay? So the area of a square is just the side length to the power of 2. But this would be how you found the area if you were given the side lengths. But if for some reason they were like, hey, the area of that square is, 25, could you find the side length? Well, that's where you take the square root of 25. Square, but it's root. I don't know if that makes more sense or makes it worse, but it's out there, okay? So here we go. Simplify the following expressions completely. So we're just finding the principal roots on these ones because it's already being established for us. So again, the question here, especially for this first one, I'll write this out, is what number times itself is 121. Now, 121 is a perfect square, so that's nice. And you have to think about this for a little bit until you get this down pretty well, right? So you could say, well, I mean, 10 times 10 is 100. It's got to be more than that. This would be 11, yep. 11 times 11 is 121. Now, we don't put both 11s there, just this one 11. And while we know that the other root is negative 11, we're not going to list this, okay, that negative 11. All right, these other two problems are kind of like order of operations types of problems, like the square root of 49, for example. You've got to look at the square root first. So square roots kind of act as parentheses. You have to do those first. Okay, so I'm not even worried or looking at this negative right now. All I want right now is the square root of 49. Now that would be 7 times 7. So the square root of 49 is 7. And then this negative that's on the outside, I would apply to the 7, okay? In fact, some students benefit from seeing that as negative 1 times that square root. And so, you know, you could say, well, negative 1 times 7, which still results in negative 7, okay? So you got to be careful on that one. Now, we know 7 times 7 is 49, 11 times 11 is 121. And this is where things get a little tricky with these square roots specifically, is we can ask ourselves, what number multiplied by itself is negative 16, right? Now, some of you guys, I think especially with pretty much no experience right now with this, sometimes we get answers like, well, 4 times 4 is 16, right? Okay, but we need it to be negative 16. That's part of the problem. And then we get this type of answer where it's like negative 4 times negative 4, but that's still positive 16. See what I'm saying? Now, this kind of goes into a different branch of mathematics right now, and we're not really ready for it. This one just has no solution, so we're just going to write D and E for now. Although in the future, you'll be expanding that a little bit more, okay? On this one, we only list the negative 7. Even though, of course, the square root of 49 has another root, the negative 7 itself, but since it's asking for the square root with the square root symbol, the radical, we only want the positive square root there, the principal root. All right, estimate between two consecutive numbers. And there's lots of different ways to do this. There's fancy ways, there's creative ways. Here's the way that I like to do it. And this gets back to kind of my main form of doing this is calculator method, okay? So here's what I'm going to do on my calculator. I'm going to type in the square root of 78. And I want the calculator to tell me what its decimal value is, okay? Now, to access the square root, you're going to have to go to the second function of the exponent button. So you got to push the second button first there in the top left, and then you're going to push this exponent button. Remember, the exponent button is one button to the left of 7 and one button up. And then you just type in the number, whatever number it is. Of course, we got 78, and now I'm going to push enter. Now, when I do that, the calculators that we're using actually, oh, I'm sorry. I said the wrong button here. This is, the button you actually wanted for this right now is the x squared button. I apologize. Now on the calculator it's showing the square root of 78, but when I pushed enter, the calculator says you wanted the square root of 78, right? There it is. I gave it back to you. But I don't want this. This would be the exact answer. I want the decimal answer, so I'm going to push this button right here. It's just one button above enter, the double arrow button, and then it will change this into a decimal. Now, we said before that when it's not a perfect square, you're taking the square root of a non-perfect square number, you get what is called an irrational number, which means that this decimal, it goes on forever and ever, but it will never repeat or terminate, okay? So, I put in the square root of 78. The calculator gave me at least as much decimal places as it can, which is, I'm just showing you what it shows me. But the question was, what two consecutive numbers is it between? Well, 8.8 is between 8 and 9. That's it. Okay, so of course, you kind of just look at the whole value here, the ones place or whatever, and then add one to it if you want, 8 and 9. Only if the question asks for it. So they'll never ask a question like this for perfect squares, because a perfect square is its own, by itself a whole value. Oh. So the square root of 45 is kind of the same thing. Again, I'll try to put the right buttons up here, but it's second, okay? And then I need to access the square root button. That's the x squared button. Second x squared will give you the square root on the screen as well if you look for that. Then just type in 45 And again, enter, that'll give you this, well, actually, this one, it's gonna show you something a little different on this one. Square root of 45, yeah, 3 square root of 5, right? This is what the calculator shows. Now, that's pretty good. It's just, that's not gonna help us with this particular problem. Again, I need the decimal to solve this one, so I push this double arrow button, just one button above, that's an arrow, by the way. And I push that, and it gives me the decimal, so 6.708203933. I'm just showing you guys all the decimals so you can, hopefully you're seeing the same thing I am.
Oh,
And hopefully I got all the decimals. But the question was, what two consecutive numbers is between? It had to be between 6. 6.7, right? Even if you're looking at a number line right here, there's 6 and 7. 6.7, you know, about right there. So this would be the square root of 45. It's right between 6 and 7. Well, not like right in the middle, but it's between. All right, see, here we go. This one wants an actual evaluation of the square root of 57 on your calculator. So even if you didn't want to use a calculator before, looks like we're going to have to in this case. And this one, even though it didn't ask for it, I'm going to go to 4 decimal places. In the past, that's about what it wanted. So again, on my calculator, I'm going to push that second button. Then I want the square root, so that's the x squared button. And then I'm typing in 57 here. And I'm going to push enter, and it's going to just give me back the square root of 57. But again, that double arrow button, just one button above the enter button, is going to change that into a decimal for us. Okay, so it shows me 7.5498344435. Very ugly, irrational number. And I said I would round to the 4th decimal place. That's the 8th right there. So what is that, the 10,000th place value? So I got to look one place value to the right. That's a 3. Now, if that was if it was 5 or more, I would add 1 to that 8, but it's not, which means the 8 will stay the same, and I can pretty much just kind of get rid of all the rest of the numbers to the right of the 8. So this ends up being 7.5498 as our estimated value for the square root of 57. You could technically say that like 7.5498, if you multiplied it by itself, you'd get somewhere around 57. But you could also say the negative of that value would also be the other root. But again, a square root symbol is specifically asking for a principal root, which is why we only show the positive value here. All right, roots and powers. Roots and powers, they are inverse operations, which is why you see on the calculator that the square root function is associated with the x squared button. That's kind of on purpose, I believe. So like if you wanted to take something and square it, if you wanted to undo that squaring with the exponent, you would square root that, okay? Now, so far, we've only talked about square roots. There are what we call third roots as well. These are cube roots, actually, which would undo something to the power of 3. See what I'm saying? Now, there's reasons for this, and in 1010, they'll go into more depth on that. But you can have higher, these are called index or indices for the roots. Like you could have something like, I don't know, the 11th root of something to the power of 11. And again, the two 11s here, essentially, you can say cancel each other out, but it becomes a phantom 1. I guess more on that later, though. All right, so, but understand that square roots and cube roots are the only ones that I'm aware of that have any kind of special names. Everything after that is 4th root, 5th root, or this one that we have here is the 11th root. Okay, but these are the only two that have special names. Kind of like with the exponents. You got x squared or x cubed. Again, you could just say x to the power of 2 or x to the power of 3 if you wanted to, but or technically this is considered a 2nd root and a 3rd root, but again, it's kind of, I don't know, maybe it's even more nerdy to say square root or cube root. I'm going to take a quick leap here just to show you why this works, okay? So, in fact, let's look at this example here, and I'll show you why this just equals x. Okay, now, to understand why it equals x, though, you need to understand that it's x to the power of 1. Remember that you get a phantom 1 exponent, you don't have to show it, which we've seen before. And this really, again, I hope that it will help you. If it doesn't make sense, just kind of ignore it, okay? So, what we do on this one, we say it's like x to the power of 11. Now, we would generally put that in some kind of parentheses there. But what a root is it's a fractional exponent, okay? So it's like saying if this 11 right here is really 1 to the 1/11th, like this. See, and if you go back to your exponent rules, you're gonna take that x base, and then you would multiply these two exponents, right? 11 times 1/11th. Well, that would just be, again, there's your phantom 1. Okay, so that's why, again, whether you say these undo each other, whether they're inverse operations, there's more to it than just saying, hey, these are inverse operations. And there's a mathematical reason for that right there. Okay? But do keep in mind, I'm not going to be showing roots with fractions like this in the future. Just understand that when I say this, because like I said, in 1010, they're going to expand on this. But for now, we just need to understand essentially this rule that your exponents, if they match with the root index, they pretty much just make each other a phantom 1 right here. So even if you got some kind of expression like this, notice that it's the x plus 6 that's to the power of 2. Now, we've already done some experience with binomials like this. You could expand this if you wanted to, but it's not going to help you. And yes, there is kind of a phantom 2 right there, which is, there's only a few occasions where there's phantom 2s. This is one of them. But really what happens is the square root is going to phantom 1 with this 2. And so all you're left with right here is just x plus 6. Now, you could keep that in parentheses if you wanted to, but I wanted to look pretty. So there it is, x plus 6. That's your final answer right there. But this would be true for any type of square root, right? And this is kind of what we've been seeing already. So there's another example. Yeah, but like if you took the square root of, say, 25, again, it's kind of like taking the square root of what would be 5 squared. See, and then the square root and the square, I just hesitate to say cancel each other out. They make each other phantom 1s, and you end up with 5 to the power of 1. Boom. All right, for square roots of fractions.
I just had to blame.
So all you're going to do if you see the square root of a big fraction like this is you're just going to break the fraction up into numerator and denominator. Now, generally, they're going to give you perfect squares as numerators and denominators, and that's why we break this up. Now, this is a rule, and this actually works. So there's more reason to this, but right now, just understand, all we're planning to do is break up the numerator and denominator into their own individual square roots, okay? So yes, an example like this one, again, don't get caught up with the fraction business because, well, fractions destroy lives, right? But I'm going to take the square root of 16 in the numerator, the square root of 121, which we've seen already, and I'm going to write this out as a fraction. Well, the square root of 16, right? What number times itself is 16? That's 4. And then the square root of 121, what times itself is 121? Well, we've already seen that is 11, okay? And that's pretty much our final answer right there. And going back to the calculator, you could type this in, even with a fraction. You push second x squared, and then you push the n over d button, and you can see inside your square root there is a fraction. Of course, you can just type in 16 over 121, and the calculator will simplify that for you as 4/11ths. Not that we needed any simplification, but it would if it needed to. So cube roots, and we already saw a cube root, right? Remember, that's a square root symbol, but you got an index now showing up here 3. And yeah, the indexes, they're a little bit smaller numbers, kind of like exponents, but in the top left instead of the top right. And they will always accompany this root, this radical symbol right here, okay? So a cube root, just at its base, is really asking you, hey, if you got a cube of some sort, and a cube, again, is like a square. It's a 3-dimensional rectangular prism. I'm going into some real nerd language here, but it's just a 3-dimensional cube, but all the lengths are the same. Okay, all the edges are the same length. That's better. And so if we said, hey, look, what is the cube root of 125? It's like saying, so for the cube thing, right? It's like saying you got a volume of a cube that's 125, but we want to know what the length of each edge is. So you take the cube root, and again, this is really asking us, I guess, oh, there it is, yeah. What number multiplied by itself 3 times is, well, in this case, 125, and in this case, it'd be 5, okay? And I'm not putting units on that just to save us a little bit of time, but the cube root of 125 is 5. So yeah, I guess I kind of spoiled the beans for this first one. Of course, the number multiplied by itself 3 times here. You can even check 5 times 5 is 25 times 5, boom, 125. So the cube root of 125 is 5, okay? And again, the second problem is kind of like what we saw with the square roots. is we got the square root of 64 here, or the cube root, sorry, of 64. And so again, what number is multiplied by itself 3 times is 64. Now, if at first right now, and I'm doing this kind of on purpose right now, just to kind of emphasize the attrition of it all, but 4 times 4 times 4 is 64. But again, that may take some thought to really figure out what that number is. So the square root of 64 is 4, and this is where, again, we take that negative on the outside and we apply it to the 4. Okay, so we get a final answer here that is negative 4. Now you got to be careful here. Remember, this is, the index is saying you got to multiply something by itself 3 times in this case to get negative 27. And where square roots, this didn't work, right? We said it does not exist because eventually you'll find out it becomes an imaginary value, which is weird that we get to calculate with something that doesn't technically exist. But with cube roots, we're fine with this. Okay, now think about this. What number times itself 3 times would be negative 27? Now the negative thing is really what I'm focusing on. And just think about this. If you took a number and multiplied it by itself 3 times, that was negative, your product would be negative. So that's why this does work with cube roots. And of course, this time it's 3. 3 times 3 is 9, times 3 is 20, oh, negative 27, sorry.
So it
But
doesn't
our
work
final
with-
answer on this one is negative 3.
does it-
So yeah, odd indices, these index roots, when they are odd, you can have negatives on the inside of that root, okay?
That's not possible.
But if these indexes are even, that is when you cannot have the negative on the inside. Now the calculator would actually tell you that. All right, the square root of 16, negative 16 on this one. I'm going to put this in the calculator, and I would urge you to do the same, just so you can see what the calculator will tell you if this is impossible for now. So again, you're going to type in the second, try to make this a little bit better. The second button in the top left, then you're going to do your, this one's just a square root for now. So that's your x squared button, and then type, you need the negative button, and then you're going to type in 16, okay? Now, no matter what you do at this point, the moment that you push enter, I forget what it says, some kind of syntax error, I think. Domain error, there we go. This one tells you, hey, this is a domain error. You're asking me to do something that I can't do. That's what the calculator, if it could talk, that's what it would say, okay? That's a domain error. Because it's saying there's nothing that times itself that you can get a negative value out of, okay? But you'll see that the calculator knows that these cube roots are okay, but we have to access that cube root, right? So I'm going to type in the cube root of negative 27 here. Let's see if we can figure this out. It's the second button. This is the one where we want that exponent button right there. That's just one button above the x squared button. And then now you'll see that it gives you a blank. Where did that go? What, second? I apologize. See, here we go. Had to have a little bit of a refresher. You have to tell it that you want the cube root, the third root. So you have to type the 3 in first. I apologize. Otherwise, it just takes the answer as the root. Okay, so 3 second, that's better. And then the exponent button. Then I can type in negative 27, right? Remember, don't forget the negative button is different than minus. Now, if I push 27 here and enter, it'll give me the actual answer that we got, which was negative 3. Which was correct. It still is correct. And in fact, the calculator, while we just did a cube root right there, in the future we're going to see that the indices are going to be increased. But again, whatever root you want, just type that number in first and then second the exponent button, and it will give you whatever root that you want. There we go. Yep. Higher indices. So higher indices, once again, it's just that this, whatever if the exponent and the index match, just pretty much get rid of that garbage and you're left with whatever was on the inside of that root. Now, in the future, this is going to create a couple extra rules, maybe some slight complications, but we can always check to make sure that things are going to work, especially, and I'm talking about when these become equations, then we got to be a little bit more careful. All right, so another thing about these indexes, again, the exponent tells you how many times something is multiplied by itself. But the index is saying you have to multiply something by itself this many times, by the that many times, whatever the index is, in order to get whatever would be a perfect, whatever that root is. So like this one, it says try to do it without a calculator. So I'm going to do it without a calculator, but I'm going to do it with the calculator as well so we can see that. But yeah, what number multiplied by itself would be 243. So I see it's not divisible. I'm used to prime factorization here. Hopefully that will help us. But 243, it's not divisible by 2 because it's not even, but it is divisible by 3 because 2 plus 4 is 6 plus 3 is 9, okay? Which means you could have divided it by 9. By dividing by 3, you'd get 81 right here. 3 is prime, and then 81 divided by, I'd say 9 times 9, neither of which are prime. And then 9 would be 3 and 3, both of which are prime, and then 9 is also 3 and 3. Now this one is nice because it just happens to be that 243, it's 1, 2, 3, 4, 5 3's multiplied together. So just to emphasize what we're doing here, you got the fifth root of 243, but I don't want to show it as 243. I want to show it as 3 to the power of, well, 1, 2, 3, 4, 5. So again, these 5's, index and exponent, make each other a phantom 1, and you're just left with the 3. Boom, that's it. But as promised, let's show how to do this with a calculator because I do like calculators. All right, so again, that's well, I got to say it's the fifth root, so I'm going to type the 5 in first, second, then I want that exponent button, and then I'll just type in 243. And then you'll see once you push enter right here, it'll tell you that the answer is just 3. Okay, so and another thing on this one, okay, so the index was odd for this, which means that even if it were negative 243, this would still work. It's just your answer would be a negative, that's all. I just want to remind you guys of that, just so if you see it on the assignment, hopefully it'll help you out. There we go, the fourth root of 625. So again, let's break up 625, see if we can do this. And I'm just looking for some prime factorization. It ends in 5, right? So I know it's divisible by 5, which is prime. But 5 goes into 6 once, 12 twice, and then 25, 5. 125, we've seen that before, but I'm going to break 125 up into 5 and 25. Okay? And then 25 breaks up into 5 and 5. Okay, and that's all my prime factors. That's a prime factorization of 625. So, again, just breaking this down so we can see what is actually happening. You got the fourth root of 625, but I'm going to show 625 as 5 to the power of 4, and then show that, again, the index and the exponent 4 undo each other, and then you just left with the 5. Okay, now if the 625 here on this one was negative, then we'd just say pretty quick, hey, there's no answer for this one, D and E, and then we would have been done. But in this case, we're in good shape there. Yeah, this one will emphasize that. So again, you could say 16, that'd be like 4 times 4, and then 4 splits up into 2 times 2. But the problem here, even though the 2's are prime, is if you made them all negative, because you'd have to remember, it has to be the same thing being multiplied by itself. You can't just make some of these negative, some of these positive. That's why this doesn't work, because negative 2 times negative 2 times negative 2 times negative 2 is positive 16. This one, D and E. And again, you don't necessarily need to do all this work to do that, all this work down here. If you saw that the index was even and your, I guess radical here is negative, is that radicand? I forget the terminology, but it's D and E. All right, simplifying radical expressions. All we're going to be doing on these, I guess for the most part, this is the product rule for radicals. But what we're going to do is we're going to take a value, even if there's something on the outside of it, and I guess we saw this with one of the problems we saw. What was it, like 3 square root of 5? But that was the square root of 45, right? Something like this. And so what happens on this is we're going to take whatever values on the inside of that square root, and we're going to break it up. We want to look for factor pairs where one of the factors is a perfect square. And again, this is why we highly encourage you to have some of your perfect squares memorized, at least up to 12. So if you need to make a list of those and put them in front of the John, whatever you got to do to memorize that, then do it, okay? Just don't, not on your windshield, because you see that a lot. But, what we do is we break 45 up into two factors, one of which will be a perfect square. Now, we know 9 is a perfect square, and then the other square is not a perfect square. That was 5. And the square root of 9 is 3 right there. That's where this comes out as 3 times the square root of 5. But we broke it up into its two factors. See how it kept the root, but we can break the factors up separately. Okay, but again, the index will tell you how many matches you need, at least if you're going to use some factor tree stuff on this, which I will do. Well, I guess I spilled the beans on this one, but I'm going to show you, okay? So square root means we need pairs. So matches, 2 matches. Matches of 2, that's better. Okay, so if you want a prime factorization on this, you could say 5 and 9, right? 5 and 9 like this. 5 is prime, and then 9 would split up into 3 and 3. Which means, again, you could say, well, just for some space, this would be the square root of 5 times 3 times 3. Again, I didn't change the value of the expression. I just changed the way it looked, right? 5 times 3 times 3 is 45. But now I see that I've got a matching pair of 3s here. And what I can do essentially is just I get to pull this out. And then since the 5 doesn't have any matches, it has to stay on the inside of the square root still. So we end up with 3 times square root of 5. Now, another way to look at this is breaking it up actually individually. So you have the square root of 5 times the square root. I'll come back to that. But then you multiply that by the square root of 3 times 3, which is, again, 3. That's a little better. But I guess part of the, I don't know, I guess, again, I'm a little bit of spoiler alert, because we did this already, right? Is if you typed in the square root of 45 in your calculator, it would have just punched this out right off the bat. So, yeah, on this one, again, the calculator will do it for you, but I'm gonna take my time a little bit on this one and say my 24. Now, notice I'm not worried about the 2 right here, although you do need to remember that it is being multiplied by the square root. And I'm gonna arrange these a little bit, hopefully a little bit better. So that would be, for me, I'd say 4 times, I guess, 6. Okay, and then 4 splits up into 2 times 2. Some of you may have used 12 and 2, and that's fine. And then 6 splits up into 2 times 3, right? So instead of this being the square root of 24, I'm going to show it as 2 times 2 times 2 times 3. And if you're still not sure that we can do that, yeah, of course we can do that. I didn't change the value of anything. I just changed the way that it looks, that's all. Because 2 times 2 times 2 times 3 is 24. Now, like we saw, this one is still a square root, so I'm looking for pairs of matching pairs, I guess. Right, so I see this matching pair of 2s. And again, I'm going to break this up. It's not very common that students would show all this work that I'm going to be doing, but if you wanted to, you could. Okay, so that'd be 2 times 2, and then 2 times 3. So you got the 2 on the outside being multiplied there. But there's my matching 2s, which really is the square root of 4, and so I bring this out as just another 2, okay? Now I still got the 2 out there in the front, and then I got this square root. Since this 2 and 3 here don't match, I'm going to multiply those to get 6. Now to make this finish, though, I actually have to do the product of 2 times 2, which is 4. So this ends up being 4 times the square root of 6. And I believe you guys understand, if you would have just typed in this original expression, the calculator would have given you this answer pretty quick. But I don't know. I don't mind doing this stuff. In fact, maybe I enjoy it more than I should. Now is a cube root, so we need a triple, matching triples on this one in order to simplify this, right? So I'm going to take my 54, and again, we'll keep the 5 there, but let's split up our 54 first. I guess I'd use, I don't know. Oh, geez. Need a little bit more thought on that one. See that? 6 and 9 on this one. Then 6 splits up into, I'm going to rearrange that just to make this come out pretty. I'm going to do it 9 and 6. That's better. Okay, because 9 splits up into 3 and 3. You'll see that the way I have this done. Again, I'm kind of doing this on purpose with my prime factors. Yeah, some of you guys see the triple threes right there. Now again, I'm gonna show a little bit more work than I think most people usually do, but this is 3 times 3 times 3 times 2. Again, I'm just showing the 54, but split up into its prime factorization. And I need a triple, a matching triple, in order to pull that out as a perfect cube. So again, just splitting this up a little bit more. There's still cube roots there, and we still got the 5. Remember, the 5 is being multiplied by the root, the cube root there. But yeah, that'd be 3 times 3 times 3. Then we got the 2, that's kind of the lone 2 there. And yeah, the triple threes again, that just becomes a 3. So now you got 5 times 3, then times the cube root of 2. All right, and then yeah, don't forget to multiply your 5 and 3 there, which is 15. So we end up with 15. You can put the multiplication there if you'd like, but 15 cube root of 2, 15 times the cube root of 2. Either way, it all means the same thing. Yeah, so on this one, it was coincidental that it was all 3s here with the cube root. But yeah, we've seen, you could have maybe three 2s or 3 4s, I guess. Now, if you use prime factorization, just understand if you get like 2 sets of triples, you'd have to pull both out as perfect cubes, or even whatever the index is, right? So like if there was 3 3s here and then 3 sets of 2, or 2 sets of triple 2s, there we go. Then I would have had 2 times 2 times 2 here, and I could have yanked that out as well. Then it would have just been 5 times 3 times 2 in this theoretical situation.